Oh, hello there! Last episode, I set up the foundations for tracing rays on arbitrary mathematical functions. This episode, we will implement proper voxel traversal for crisp block edges. All blocks seen will be held in video memory. The goal of a ray tracing renderer is to spend the minimal amount of time calculating intersections with the world geometry. This requires an immense amount of optimization. Voxels are useful for ray tracing because they are uniform. Optimization is all about reducing the unknowns, and cubes achieve that simplicity by being inherently congruent. By aligning all voxels to a grid and a whole number coordinate system, the problem becomes even simpler. The most famous approach for intersecting a uniform grid of cubes is the Digital Differential Analyzer, or for short DDA. DDA is an algorithm where you compare a ray to a series of flat planes and determine the next closest intersection given a current block position. This is as simple as y equals mx plus b from algebra class, albeit with consideration of pesky divide by zero errors. The difficult part is how you sample the memory following any DDA solution. One must consider literal edge cases and corner cases where block seams may be missed entirely. This introduces a variety of visual artifacts. Artifacts refers to any side effect of the rendering process. In our case, we see fireflies, speckles of mismatched color that appear for a single frame while moving the camera. This is extremely undesirable for real-time graphics. Even if the traversal algorithm considers edge cases, there is also an inherent mathematical error in decimal math when ran on a computer. This causes block face intersections to sample two adjacent blocks randomly, depending on the fine decimal information stored in the corresponding camera ray. The result is strange circles of noise that roughly correspond with the field of view, appearing staticky. My solution is to store an integer coordinate as the current block, then step one block at a time across the first valid axis. Corner cases will result in 3 arbitrarily ordered planar steps instead of one false step through a seam. The result is an octahedron-shaped frustum surrounding the camera. This works fabulously for perfect grids of voxels, but not for voxels varying sizes. That's a problem for next episode. We can use the amount of planar DDA steps as a measure of distance once an intersection is found. By sending this metric to a texture, we get a grayscale version of the scene geometry. This is called the depth value, and is extraordinarily useful for applying post-processing filters and deferred shading calculations. Examples include fog, distance blur, and levels of detail. The rainbow gradients on voxels seen in this video represent UV coordinates used for texture and shadow calculations. Debugging for GPU code is often done by converting data layers to contrasting colors which can be displayed on the screen texture. Any visual exceptions indicate a bug in the code. I resolved the DDA precision errors and want to set up the foundation for larger voxels to be traversed using the same logic. As pre-calculated on the CPU, larger voxels are solid if any of their 8 corresponding child voxels are solid. Preferring expansion like this prevents gaps from forming in the geometry when changing voxel size. We can dynamically convert the DDA algorithm to operate on a coordinate grid of varying sizes to calculate ray steps on any layer. Finally, I added a source texture from the Unity camera with the intent of adding a skybox. I accidentally added this ghost effect, which is achieved when the pixels are not reset every frame. Next episode, we will return to our infinite scene to add dynamic level of detail, textures, and ambient occlusion shadows. See you then!